Okay, so this is where everything kind of comes together. We're going to be solving exponential and logarithmic equations. A couple of things we want to recall is if we have a to the x equals a to the y, this is true if and only if x equals y. If log base a of x equals log base a of y, this is true if and only if x equals y. And a to the log base a of x equals x, and log base a of a to the x equals x. So those are some of our properties from earlier. Those are going to play a big role in this, as well again as our ability to rewrite equations from logs to exponentials and vice versa. So if we have 3 to the x equals 27, we want to solve this for x. There are many approaches. I want you to try this on your own. You could actually do this without doing any work, but then we're going to look at a lot of the different approaches just so we get an idea of how to go about doing this. So pause the video, answer this, unpause when you're ready to hear me talk more. Alright, well maybe you just said to yourself, okay, I just know 3 to the third is 27, so that's my answer. But what I want to point out is that thought process is really doing something like this, where I can say, okay, 3 to the x equals 3 to the third, because 27 is 3 to the third. So what this technique is doing is it's getting a common base. And then we know that if the bases are equal, the exponents have to be equal. So then I can say x equals 3, right? Another way would be to rewrite this as a log equation. So if I convert this to a log equation, it becomes x equals log base 3 of 27. So what is log base 3 of 27? Well, I can change the base into natural log or a common log, and I know x equals natural log of 27 over natural log of 3, and then if I type that into my calculator, I get 3. Another way to do this would be to take the log of both sides. This is going to turn out to be very similar to what I have here in the green. I chose natural log in this case, but again, you could really do any log you want. So if I take the natural log of both sides, now using my properties of exponents, I can bring the x down. So I have x natural log of 3 equals natural log of 27, divide by natural log of 3, and then same thing, I get x equals 3. Alright, next one, same thing. Try this on your own. We'll look at multiple approaches. Pause the video, unpause when you're ready to check. Alright, so simplest thing to do, if possible, is to get a common base. So I know that 4 is 2 squared and 9 is 3 squared, so I can change 4/9 into 2 over 3 quantity squared. So I have 2/3 to the x equals 2/3 squared, so I know x has to equal 2. Alright, what's another approach? Well, in this case I chose to take the log base 2/3 of both sides. So if I do log base 2/3 of 2/3 to the x equals log base 2/3 of 4/9, using my properties of exponents, bring down the x. I know that log base 2/3 of 2/3 has to equal 1. That's a property of my logs. So I know x equals log base 2/3 of 4/9, and then again using change of base, I changed it to common log this time. Log of 4/9 over log of 2/3. If I type that into my calculator, I get 2. So the point of showing you this is, yes, that's way more work than what I did over here, but sometimes this is the technique we're going to have to use, because what if this was 3 over 9? That's a bad example. What if this was 5 over 9? Well, then I cannot use this technique, so I have to do something along these lines. Okay, so that's why I'm showing you both methods. Let's look at another one. Natural log x minus natural log of 5 equals 0. Go ahead and solve this. Again, multiple techniques. Pause the video, unpause when you're ready to check. Okay, so the simplest thing to do here is to add natural log of 5 to both sides. So then I get natural log of x equals natural log of 5. So then by properties of equality, I know x has to equal 5. And maybe you figured that out without even adding it over, because common sense would tell you if I take two things and subtract and get 0, they have to be the same, right? Okay, but again, well, what if it wasn't that obvious? Another technique would be to combine the two logs into a single log. So since this is subtraction, I can make this natural log of x divided by 5 equals 0. And now I can change it from a log equation into an exponential equation. I know natural log is log base e, so this becomes x over 5 equals e to the 0. So again, this right here, going from the blue to the purple, most important technique you need to know how to do in all of the world. Not really the world, but in this unit. So then I know e to the first is 1, so x over 5 equals 1, multiplied by 5, x equals 5. One thing I want to point out, now if the original equation is a log equation, meaning that there are logs in the original equation, we need to check for extraneous solutions. If the original equations are exponential equations, we do not need to check for extraneous solutions. But if the original equations are log equations, there's a potential to get extraneous solutions, so we need to check. Really, all we're checking for is we need to make sure we are not taking the log of a negative or 0. Next, e to the x equals 4. Solve. Pause the video. Unpause and check. X equals natural log of 4. That's it. So this was an exponential equation that was not obvious. Okay, I can't change 4 into something base e. I mean, I can. It's going to be a lot of work. Well, never mind. Let's just... Anyway, so it's not easy to change 4 into base e because, well, e is e. So I can just rewrite this as a log equation. So I know x equals natural log of 4. Log base 5 of x equals negative 3. Pause the video, solve. So here, rewrite the log equation as an exponential equation. So x equals 5 to the negative third, but 5 to the negative third is 1 over 125. Alright, what about 2 times 5 to the x equals 32? Go ahead and solve that. Pause the video, and pause when you're ready to check. Okay, so first thing we want to do here is isolate the exponential piece. So the exponential piece is 5 to the x. So we cannot multiply the 2 and the 5. You know, our order of operations tells us the exponent comes first. So I divided by 2. So I end up with 5 to the x equals 16. Now I have an exponential equation. It's not going to be convenient to change 16 into something that is base 5. So I just change it into a log. And I could write my answer as either x equals log base 5 of 16. That is perfectly acceptable. Or you could do a change of base and do natural log of 16 over natural log of 5, or log 16 over log 5. Any of those would be acceptable. Alright, try 8 times 3 to the 6 minus x equals 40. Pause the video, unpause when you're ready to check. So here we end up with x equals 6 minus the natural log of 5 over the natural log of 3. There's other ways to write the answer though. Again, our first thing though is isolate the exponential piece. So if we have an exponential equation, isolate the exponential first. So I divided by 8. So 3 to the 6 minus x equals 5. And now I chose to take the natural log of both sides. I could have also changed this into log base 3 of 5. That's perfectly fine. So when I did that, when I took the natural log of both sides though, now I can bring down my exponent. So 6 minus x equals natural log of 3 minus, or 6 minus x times natural log of 3 equals natural log of 5. Divide by natural log of 3, and then I can subtract 6 and divide by negative 1. So that's how I get x equals 6 minus natural log of 5 over natural log of 3. But again, if you chose to do log base 3, you would have x equals 6 minus log base 3 of 5. Perfectly acceptable. Same answer. Next one, which conveniently is the last one as well. So if I have log base 9 of 4 plus x equals log base 9 of 2x minus 1, go ahead and try and solve this. Pause the video, unpause when you're ready to check. Alright, so here again I'm going to show you 2 ways to go about this. One is definitely less work than the other. So remember our property of logs where we said, okay, if I have log of x equals log of y, then x has to equal y. Well, that's the scenario I have here. Log base 9 of 4 plus x equals log base 9 of 2x minus 1. This is only true if 4 plus x equals 2x minus 1. So I can go ahead and essentially drop the logs and set those equal to each other. Only because the bases are the same. If the bases are different, now it becomes a different problem. But now I can just do some basic algebra and I can solve and I get x equals 5. Don't forget to check for extraneous solutions, and what we're checking for is when I plug that back in, does this quantity, what I'm taking the log of, become negative or 0? And I have to check in every single log term, because if it fails in one of them, then it fails. So that's the easier way to do the problem. Well, what if I didn't recognize that? That's okay. Then the other way to go about this would be to subtract one of the logs to the other side. So I can say log base 9 of 4 plus x minus log base 9 of 2x minus 1 equals 0. Because I have the same base, I can combine these into a single log with division. So log base 9 of 4 plus x over 2x minus 1 equals 0. Now I get rid of the log by changing this into an exponential equation. So 4 plus x over 2x minus 1 equals 9 to the 0th power. Anything to the 0 power is 1. Multiply both sides by 2x minus 1. This is a rational equation now. And then solve again, and I get x equals 5. All right, so a couple of strategies. When solving exponential equations, if we cannot get a common base, then isolate the exponential and rewrite it as a log equation. Take the log of both sides if you need to. You know, kind of use your best judgment, whatever you're more comfortable with. We have options in this case. If we are solving a log equation, again, try to isolate the log if possible. Rewrite it as an exponential equation or exponentiate both sides, and then solve. If the original equation is a log equation, though, don't forget to check for extraneous solutions as well.